Yeah, hello everyone. Good afternoon. Good evening. So today we will discuss about the chemical bonding and its molecular structure. Part one. Okay. So it is a crash course, and we will discuss this today and tomorrow. So today we will try to cover some topics, and the topics that we are going to cover today, they are chemical bond and its types of overlapping, hybridization, and BSc-PR theory. Okay. Coming to the introduction, the attraction between the two or more than two atoms in a molecule is known as chemical bond. So why do atoms combine to form a bond? To minimize the energy and to attain the stability. So the chemical bond is formed from the atoms to attain the stability by releasing the energy. Okay. Now what are the types of chemical bond? So it is classified into two. One is a strong bond and the other one is a weak bond. Strong bonds are again classified into three: ionic bond, covalent bond, and metallic bond. These three bonds are called as strong bond. And hydrogen bond and van der Waals forces are called as weak bond. So for strong bond, as the name suggests, the bond energy is very, very high. It is approximately 200 kilojoule per mole. So the interatomic energy, they are interatomic in case of strong bond, and in case of weak bond, they are intermolecular. Hydrogen bonding, it is between two molecules mostly. And van der Waals force is also between two atom or two molecule. So that is intermolecular and this is interatomic. And here the energy required to break the bond is very high, and the energy required to break the bond in case of hydrogen and van der Waals is very, very less, just around 2 to 42 kilojoule per mole only. Okay. For hydrogen bond in case of neutral molecule, it is just around 8 to 42. And van der Waals force is the very weakest force among all. So the energy required to break it is just 2 to 8 kilojoule per mole. So this is about the types of chemical bond. And talking about the covalent bond specifically, the covalent bond can be of sigma type, pi type, and coordinate type. So sigma bond, pi bond. These two bonds are formed by the equal sharing of electron, but coordinate bond is formed by the unequal sharing of electrons. Okay. So we will discuss the overlapping of the sigma and pi bond in the next slide. So let us move on to the next topic, that is types of overlapping. There are two types of overlapping: axial and sideways. Axial overlapping is otherwise called as head-on overlapping or coaxial overlapping. Okay, so this axial overlapping only forms the sigma bond. Okay, the sideways overlapping of orbital or collateral overlapping of orbital forms the pi bond. Now let us see some examples for these two types. Moving on to the first type, that is head-on overlapping. So there are three types of head-on overlapping and three types of sideways overlapping. The first three types of head-on overlapping are SS overlap, SP overlap, and PP overlap. The SS overlap is the overlapping of two s orbital. You can see the hydrogen as an example here. The 1s orbital of the first hydrogen overlaps with the 1s orbital of the second hydrogen. Both of the hydrogen has one electron each. They overlap to form a sigma bond. And one s orbital is overlapping with one p orbital. Like in case of HCl, the last electron of chlorine will be there in one of the p orbital, and hydrogen will have one electron in one s orbital. So they overlap in a sideways manner to form the sigma bond. SP overlap. SP sigma bond. And talking about PP sigma bond, p orbital of both fluorine, last electron will be there in p orbital of fluorine, that is 2pz orbital will have one unpaired electron. So two fluorine atom, they will have two unpaired electron. They now overlap in a head-on manner to form the PP sigma bond. Okay, so basically the sigma bonds are formed from the head-on overlapping of the corresponding s orbital and p orbital. Got it? Now moving to the sideways overlapping. The sideways overlapping, there are also three types of sideways overlapping. One is p pi overlap. One p orbital overlaps with the other p orbital, which you can see in the slide. They overlap in a sideways manner to form the p pi overlap. And one orbital One p orbital overlaps with the d orbital also. D orbitals are double in shape, right? So they overlap. Positive phase and negative phase, they overlap in the plane to give the d pi overlap. And two d orbitals, they overlap in a sideways manner to give the d pi overlap. Okay. So two lobes of each d orbital, they overlap to form this d pi pi bond. Clear? So these are the two types of overlapping. Now the third topic is hybridization. What is hybridization? Intermixing of atomic orbital is called as hybridization. Of an atom of nearly same energy but different shape to form entirely new orbital, equal in number of mixed atomic orbital having identical shape and energy. The newly formed orbitals are called as hybridized orbitals or hybrid orbital. Suppose if one s orbital and three p orbitals are mixing with each other, we get sp3 hybridized orbital. So totally 4 atomic orbitals are mixing. So 4 sp3 hybridized orbital will form. Okay. If one s orbital and if 2 p orbitals are mixing with each other, then it would result in sp2 hybridized orbital. So since 3 atomic orbitals are mixing with each other, 3 sp2 hybridized orbital will form. Okay. So this is the concept. And there are also different types of hybridization. If S and P alone are mixing with each other, it leads to sp, sp2 and sp3 combination. And if d orbital is also mixing with s and p, then it leads to 3 more types: sp3d, sp3d2, sp3d3. Now, how to find out the hybridization of an element easily? What is the trick to find out the hybridization? You can use this formula, electron pair formula. It is equal to bond pair plus lone pair. It is equal to bond pair plus lone pair. If the electron pair in total, if it is equal to 2, then the hybridization is sp. If it is 3, sp2. If it is 4, sp3. If it is 5, sp3d. If it is 6, sp3d2. And if it is 7, it is sp3d3. So I'll give you an example. Suppose, let me take NH3. So nitrogen has one lone pair, right? So let me draw the structure. So 3 NH bond and 1 lone pair. So now we have to calculate the electron pair of this NH3. Now how many bond pairs are there? How many bonds are there? 3 bonds. And how many lone pair? Only 1 lone pair. So 3 plus 1 is 4. Electron pair is 4. If the electron pair is 4, then the hybridization is sp3. So the hybridization of this nitrogen is sp3. Okay. So one more example I will take. Water. So H2O. So H2O. Oxygen has 2 lone pair. So what is the electron pair? Number of bond pair is 2 and number of lone pairs again 2. 2 plus 2 is 4. So again the hybridization of oxygen is sp3. So this is how you can find out the hybridization of an element so easily without going for the detailed explanation. Okay. So now the last topic for today is VS-EPR theory. So VS-EPR means valence shell electron pair repulsion theory. Okay. So using this theory, we can predict the shape of the molecule and the geometry of the molecule. So we have 2 different cases. One is the type of molecule which have 0 lone pair, and the other case is the molecule which have 1 lone pair, 2 lone pair, and 3 lone pair. So there are 2 cases. One is lone pair equal to 0 system, and the other one is lone pair not equal to 0 system. First, let me discuss the first type, that is the geometry of molecule in which the central atom has no lone pair of electron. So I'll give you one tabular column. So if the number of electron pair is equal to 2, the arrangement of electron pair would be like this, AB2 type. So the examples are BCl2 and HgCl2. You can see it is linear. For AB2, it is linear. And for AB3, it is trigonal planar. Trigonal planar. Boron at the center and 3 fluorines are in the plane. Trigonal planar. And for the number of electron pair, if it is equal to 4, it is tetrahedral. It is tetrahedral. The bond angle in case of linear is 180 degree, which is very important. And for trigonal planar, it is 120. And tetrahedral bond angle is very, very important, 109.5 degree. Okay. Yes. Yeah, good evening, Swapna. Good evening. So I'm discussing the VSEPR theory. Okay. So today in the crash course, we are learning the chemical bonding lesson. And today and tomorrow also we will continue this lesson. And today I have discussed the introduction of chemical bond and some types of overlapping and hybridization. Now I am discussing with the VSEPR theory. Okay. So coming to the next thing, if the number of electron pair is equal to 5, example is PCl 5, the geometry is trigonal bipyramidal. Trigonal bipyramidal. Phosphorus at the center, 3 chlorines are in the plane, one is above the plane and the other one is below the plane. Trigonal bipyramidal. And the bond angle, you see, 2 different bond angles are there. One is 120 degree and the other one is 90 degree. Okay. And the last, if the number of electron pair is equal to 6, then the geometry is octahedral. S of 6 is the taken as an example. Yes, sulfur at the center, 4 fluorines are in the square plane, one is above the plane and one is below the plane. So it forms the octahedral type of geometry. So these are the systems in which the central atom has no lone pair. So now we will discuss the second case, that is the molecules or ions with central atoms having one or more lone pair of electron. Okay, one or more lone pair of electrons. So the first type is AB2E. AB2E. For the system which is having the lone pair, whose lone pair is not equal to 0, its shape and geometry will be different. Shape is not equal to geometry. So how to find out the shape? Without considering the lone pair, if you see the molecule, it will give you the shape. And if you consider the geometry, it will give you the, if you consider the lone pair, it will give you the geometry. If you do not consider the lone pair, it will give you the shape. And if you consider the lone pair, it will give you the geometry. Okay. So for this AB2E type molecule, if for example, SO2, this is sulfur, double bond O and double bond O. And one lone pair is at the sulfur. Now, if I don't see this lone pair, it is giving bent. So bent is the shape. And if I consider that lone pair, it is giving me the geometry. That is trigonal planar is a geometry. Okay, very easy. And E represents the lone pair here. And the second type is AB3. AB3. 3 bond pair and 1 lone pair. Example NH3, which we have already discussed. So if you do not consider the lone pair, it will give you trigonal pyramidal. If you consider the lone pair, it will give you tetrahedral. And AB2E2, H2O, bent shape and tetrahedral geometry. And AB4E, if you see, sulfur at the center and 4 fluorines are like this. And one of the lone pair of sulfur, it is occupying the equatorial position. Okay. So if you do not see that lone pair, if you don't consider that lone pair, it will give you seesaw shape. And if you consider that, it is giving you the trigonal bipyramidal geometry. Okay. Lone pair they always occupy the equatorial position to minimize the repulsion. Bond pair, lone pair, repulsion. It always tries to occupy, lone pair always tries to occupy the equatorial position. It will occupy the horizontal position. Okay. And coming to the AB3E2 type, example ClF3, chlorine at the center, 3 fluorines like this. They take the T-shaped thing, and if we consider this lone pair, it is giving us the trigonal bipyramidal geometry. Okay, moving on to one more type, AB5E. So bromine at the center, 4 fluorines are occupying the square plane, and one fluorine is above, and one of the lone pair is occupying the below part. Okay. So if you don't consider the lone pair, it will give square pyramidal shape, and if you consider the lone pair, it is giving you the octahedral geometry. Okay. The last type is AB4E2, HCF4, xenon at the center. 4 fluorides are occupying the 4 corners of the square plane, and one lone pair is occupying above and the other lone pair is occupying below. So it is square planar shape and octahedral geometry. Okay. So this is about the shape and geometry of the molecules according to VSEPR theory. Now, based on this hybridization, VSEPR and orbital overlapping concept, we will see some previous year's questions of JEE and NEET. Okay. So moving on to the first question. Most of the questions from this VSEPR theory of they are of match the following type only, which is very, very easy for you. So you can solve it so easily. So moving on to this, list 1 has NH3, ClF3, PCl5 and VRF5, and we have seen the geometry of all these just now in the previous slides, right? So what is the geometry of NH3? It is trigonal pyramidal. Actually, these are the shapes, not the geometry, right? So they are the shape. So NH3, if you see, to find out the shape, we should not see the lone pair. So it is trigonal pyramidal. A goes to 3 and the ClF3 I already told you. ClF3 is T-shaped, and PCl5. It doesn't have lone pair. So it is trigonal bipyramidal shape, and BRF5 is square pyramidal. So A3, B4, C2 and D1. So option C is the correct answer for this. Okay. Now coming to the next question. Among the following, which one will have maximum lone pair repulsion? The compound which is having more number of lone pair will have the maximum lone pair repulsion. So the structure of ClF3 is T-shaped and ClF3 has 2 lone pair. So the number of lone pair is equal to 2. And IF5, if you see, IF5 is having 1 lone pair. So the number of lone pair of IF5 is 1. And SF4, which is having seesaw shape, sulfur is having 6 valence electron, 4 has gone for bonding, and remaining 2 is present as 1 lone pair. Lone pair is equal to 1. And xenon is having 8 valence electron, right? Only 2 has gone for bonding. Remaining 3 is present as lone pair. So the number of lone pair in case of HCF2 is 3. So the maximum number of lone pair is observed in HCF2. So in that molecule only maximum lone pair repulsion will be present. Got it? Very easy. Now coming to the next question. BF3 is planar and electron deficient compound. The hybridization and number of elements around central atom. Boron is the central atom. So this is the structure of BF3. And we have to find out the hybridization first. So to find out the hybridization, I told you we have to find out the electron pair. Electron pair is equal to bond pair plus lone pair. So boron is having 3 bond pair and 0 lone pair. Electron pair is equal to 3. If it is equal to 3, then the hybridization is sp2. Right? Now the number of elements around, it is not actually elements, it is electrons. The number of electrons around central atom. So there are 3 bonds. Each bond has 2 electron. Number of electrons around BF3 is 6. So sp2 and 6 is the answer. Option D. Option D is the correct answer for this question. Okay. Now coming to the next question, which is again of match the following type. It's an easy question again. PCl5 is trigonal bipyramidal. A goes to 4. SF6 is octahedral. SF6, right? So 4 at the square plane. 4 in the square plane, 1 above and 1 below. This is SF6, which is octahedral in shape, and BRF5 is square pyramidal and BF3 is trigonal planar. Option B is the correct answer. The number of sigma and pi bonds in pent2ene 4-ine. So pent means 5 carbon should be there. So this is carbon number 1, 2, 3, 4, and 5. Between 2 and 3, there is a double bond. Between 4 and 5, there is a triple bond. Okay. So now satisfy with the hydrogen. So to the first carbon, we have 3 hydrogen. To the second carbon, we have 1 hydrogen because already 3 bonds are there. Here also only 1. Here no hydrogen and here 1. So each carbon should have 4 bonds, right? So accordingly, hydrogens are given. And now find out the sigma. All the single bonds are sigma. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So there are 10 sigma bond and 1, 2, 3 pi bond in this molecule. So 10 sigma and 3 pi bond. So the correct answer is option C. 10 sigma bond and 3 pi bond. Okay. Now, in the structure of ClF3, the number of lone pair of electrons on central atom. What is the number of lone pair of chlorine, central atom, and ClF3? It is 2, right? There are 2 lone pair. Correct answer is option B. Okay. Now, it's a statement type question. Statement 1 says that SO2 and H2O both possess V-shaped structure. Both possess V-shaped structure. Is that right? Will both the compound possess the V-shaped structure? Yes. The bond angle of SO2 is less than that of H2O. So let me show you the structure. So this is the structure. Both have V-shaped structure. So statement 1 is correct. Bond angle of SO2 is little bit greater than that of H2O. Okay. So because of the 2 bond pair of electron and the size of the sulfur, the bond angle increases. But here the second statement is incorrect. So it is actually more than that of H2O, right? So statement 1 is correct, but statement 2 is incorrect. So option C is the correct answer. Okay. Now coming to one more match the following type. Here you see more number of match the following type questions only is being asked from this theory. H3O plus. So what is the geometry of H3O plus? So this is H3O and 1 lone pair will be there. So this is H3O plus. Actually, oxygen will have 6 valence electron. Now 3 has gone for bonding, 1 it has lost, and 2 more is there, which is present as 1 lone pair. Acetylide anion, it is C2 minus. C2 minus is acetylide anion. C triple bond C minus and minus. So it is linear. It is linear. Acetylide anion is linear in shape. And NH4 plus, if you see, it is tetrahedral. NH4 plus, tetrahedral. And the ClO2 minus, Cl double bond O, double bond O. So it is bent. It is bent. So A3, B2, C1 and D4. So option B is the correct answer for this. Okay. Let's discuss one more. So 5 statements are given and we have to find out the correct statements. Okay, 5 options and we have to find out the correct options. So coming to the first statement, the number of lone pairs on oxygen in OF2 molecule is 2. Okay, let me draw the OF2 molecule. So this is OF2 and in OF2 there are 2 lone pairs. Okay, this is the structure. Number of lone pair is 2. So option A is correct. The FOF bond angle is less than 104.5 degree. So in water, if you see, it is H2O, the bond angle is 104.5 degree. But here fluorines are there. So the lone pair repulsion will be there and it will be less. FOF bond angle is less than 104.5 degree. So that is also correct. Okay. Coming to the oxidation state of oxygen, oxygen is bonded with the more electronegative element fluorine. So fluorine will gain that electron, oxygen will lose that electron. Here also fluorine gains and oxygen loses its electron. So the oxygen is acquiring the +2 state, but here it is given as -2. So it is the incorrect option. And the molecule is bent V-shaped. Yeah, it is bent V-shaped only. It is also correct. Molecular geometry is linear. No, molecular geometry is a kind of distorted tetrahedron. So again, it is an incorrect one. So the correct statements are A, B, and D. So option B is the correct answer for this question. Okay. Coming to the next question. Again, match the following type. So IF7, the number of lone pairs on pairs of electron on central atom. How many lone pairs we have to find out? So IF7, iodine is halogen and it has 7 valence electron, in which all the 7 electrons has gone for bonding. So the number of lone pair is equal to 0. A goes to 4. And coming to ICl4, so iodine, 7 valence electron, it has formed 4 bonds and has gained 1 electron also. So 7 plus 1, 8, totally 4 bonding and 4 lone pair, 2 lone pair. 4 in lone pair, 2 lone pairs. So ICl4 has 2 lone pair. IF7 has 0 lone pair. Xenon hexafluoride. So xenon hexafluoride will have 1 lone pair because the valence electron of xenon is 8. 6 has gone for bonding. Remaining 2 electrons are there. They will be present as 1 lone pair, which leads to the distorted octahedral geometry. So it has 1 lone pair. And coming to HCF2, it is linear in geometry shape, in which it has 3 lone pair. Okay, so HCF2 will have 3 lone pair. So the correct option is C. A4, B3, C2, D1. C is the correct answer. Now the number of lone pairs of electrons in the central atom of SCl2, yeah, starting with SCl2, sulfur belongs to oxygen group. It has 6 valence electron, 2 has gone for bonding, and remaining 4 is present as 2 lone pair. So the number of lone pair of sulfur is 2. And coming to O3, so this is O3. There is 1 lone pair in O3, actually +1, -1. So the number of lone pair in O3 is equal to 1. And coming to ClF3, which is having T-shaped, it will have 2 lone pair. So the lone pair is equal to 2. Chlorine belongs to 17th group, 7 valence electron, 3 has gone for bonding, remaining 4 is present as 2 lone pair. And coming to SF6, sulfur, 6 valence electron containing system, all the 6 electrons are used for bonding. So the number of lone pair is equal to 0. So 2120 is the answer. Option B is the correct answer for this question. Okay. Now coming to the next question. Again match the following. BRF5 square pyramidal. CrF6 3 minus. CrF6 3 minus. Octahedral. Okay. It is octahedral. O3 is bent. PCl5 is trigonal bipyramidal. So option C is the correct answer. Consider the species and choose the correct option. So CH4, NH4 plus and BH4. So we have to find out whether they are isoelectronic and whether the structures are same, okay, or not. So CH4. So this is the structure of CH4. The total number of valence electron, if we want to calculate, or the number of electron for carbon, it is 6. 4 hydrogens are there, so it is equal to 10. And for NH4 plus, if you see, so nitrogen is having, okay, let me go with the valence electron concept. So carbon is having only 4 valence electron. So 4 plus 4 would be 8, right? So the total number of valence electron here, it is for carbon it is 4. 4 plus 4 is 8 valence electron. And for nitrogen it is 5. 5 plus 4 hydrogen, but it has lost one electron, so it is again 8. And coming to BH4, the valence electron of boron is 3, but boron has gained one electron. 3 plus 4 plus 1, so it is 8. So all the 3 species are having 8 electrons, so they are isoelectronic, and all these are tetrahedral. You see the structure, all are in tetrahedral structure. So option B, they are isoelectronic and all have tetrahedral structures is the correct answer. So the number of lone pairs of electrons on central atom and the shape of BRF3 molecule is, BRF3 is identical to CLF3. So CLF3 is T-shaped, right? So the same way, BRF3 is also T-shaped with the 2 lone pair. Little bit bent T-shape, we can say, kind of bent shape like this. It will be slightly bent. Okay, so 2 lone pair with the bent T-shape. Coming to the next question, in the structure of SF4, the lone pair of electrons on sulfur is lone pair of electron. So SF4, we all know it is seesaw-shaped molecule. The lone pair occupies the equatorial position. Okay, the lone pair occupies the equatorial position. So either option A or B should be the correct answer. There is only one lone pair. There are 2 electrons in that one lone pair. And how many lone pair bond pair? This is one lone pair bond pair repulsion. And this is another lone pair bond pair repulsion. So totally there are 2 lone pair bond pair repulsion at 90-degree angle to each other. Okay, and lone pairs are occupying the equatorial position. So the correct answer is option A. Correct answer is option A. Now identify the incorrect statement for PCl5 from the following. So we know that PCl5, in PCl5, phosphorus has 0 lone pair and it is trigonal bipyramidal in geometry. Okay, let's start from the first option. In this molecule, orbitals of phosphorus are assumed to undergo sp3 dehybridization. Yes, the electron pair, if we calculate, the number of bond pair is equal to 5. Lone pair is 0, so it is equal to 5, which leads to sp3 dehybridization. That is correct. We have to find out the incorrect statement, right? Geometry is trigonal bipyramidal. Yes, that is also correct. PCl5 has 2 axial bonds stronger than 3 equatorial bonds. No, equatorial bonds are stronger than axial bonds. Equatorial bonds are stronger than axial bonds. So that is an incorrect statement. And all the 3 equatorial bonds of PCl5 lie in the same plane. Yes, that is correct. All the 3 occupies the same plane. So option C is the incorrect statement given. Okay. Now one more question that match the following type. We have to find out the hybridization. Okay, let's start from SF4. So SF4 is seesaw shape again. So let us calculate the electron pair. Electron pair is equal to 4 bond pair and 1 lone pair. So it is equal to 5. So it is sp3d. Okay, sp3d. Coming to IF5. IF5. Among the 7 valence electrons of iodine, 5 has gone for bonding and remaining 2 is present as lone pair. So the number of electron pair is equal to 5 bond pair, 1 lone pair. It's totally 6. So it is sp3d2. sp3d2. Okay. Now NO2 plus. NO2 plus. NO2 plus. So the electron pair is 2 bond pair and 0 lone pair. So it is equal to 2. So it is sp. It is equal to sp. And coming to NH4 plus. So nitrogen has 4 bond pair of electron, 4 bond pair and 0 lone pair. So it is equal to 4. In which sp3. sp3. It is sp3. So sp3d, A goes to 3 and B goes to 1, C goes to 5 and D goes to 4. So it is given in option C. Just find out the hybridization using electron pair equal to bond pair plus lone pair formula and find out the answer very easily. Okay. Fine. Coming to the next question. The hybridization of the atomic orbitals of nitrogen in NO2 minus, NO2 plus and NH4 plus respectively are. Yeah. So let's start from NO2 minus, NO2 minus. So nitrogen has gained one electron. So here if you see the electron pair, 2 bond pair, 2 sigma bond and 1 lone pair, right? So it is equal to 3. So it will be sp2. And coming to NO plus, just now we have calculated. So there are 2 electron pair and 0 lone pair. It is equal to 2, which leads to sp hybridization. And NH4 also we have seen how many bond pair? 4 bond pair and 0 lone pair. So 4 plus 0, which is equal to 4, sp3. So sp2, sp and sp3. Okay. Option D is the correct answer for this. Option D is the correct answer. Coming to the last question for this session, it is of assertion and reason type. So assertion says that the HOH bond angle in water molecule is 104.5 degree. Yes, that is true. The bond angle in case of water molecule is 104.5 degree. It is very important to be memorized and that is correct. The lone pair repulsion of electron is higher than bond pair repulsion. That is also correct. The repulsion order follows this, no? Lone pair is greater compared to lone pair and bond pair, which is higher than bond pair and bond pair. This is the order of repulsion which we have to use. Because water molecule has 2 lone pair, this lone pair repulsion would be very high so that the bond angle decreases from the normal tetrahedral bond angle, which is 109.5 degree. Okay. So because of this reason only, the HOH bond angle in water molecule is less. So both A and R are true, and R is the correct explanation of A. R is the correct explanation of A. Hi Rachinita, how are you? Seeing you after a long time. So this is the last question for today. So I think Rachinita, you can go through the video which is there in the channel and you can revise this chemical bonding lesson from that. And tomorrow we will continue this chemical bonding lesson. And in that, we will discuss the bond properties, all the bond strength, bond length, those things. And we will discuss about the molecular orbital theory also. Okay, tomorrow we will see that in this lesson. And this part 1, you can see from the YouTube. Okay. Rachinita, is that okay? Try to join on time. Try to join at 4 p.m. Okay, so that you will not miss the class. So here I am ending the class. Go through the video, and if you are having any doubts, let me know in the next class. Is that okay? Okay, thank you so much. Thank you so much for listening the lecture. Bye-bye. I'm ending up here.